Hi everybody, welcome back. Last time we ended up in section 10.1 when we were talking about correlation. And if you remember at the beginning of that section I was talking about chapter 10 and what we were going to be discussing in chapter 10. And one of the other items that we were going to be talking about in chapter 10 was this topic on regression. We needed to know what is a linear regression and what do we use it for. All right, so in here, we're going to start off with the definition for regression. This says that given a collection of paired sample data, the regression equation, which is given by this here, is given by y hat is equal to b naught plus b1 x. Algebraically describes a relationship between two variables. Now, this is, again, it seems very abstract at this moment in time. However, I'm going to ask you all to recall a certain topic from algebra class. I know it's kind of a long ways away, far away, but, you know, let's go ahead and let's talk about this. All right, so a linear equation from algebra class looks like this. Y is equal to mx plus b. Well, in this particular case, y is equal to mx plus b, we know that b is the y-intercept and m is going to be the slope. So in here, b is the y-intercept and m is the slope. Now, why does this pertain to us, or why do we care about it? The reason we care about this is because this term here, mx, is really this term here, b1x. So these are the exact same terms. And then we also have that my y-intercept is just this y-intercept for b naught, or b sub 0. So naturally, we're still getting this exact same equation that we did from algebra class, except now we're going to use it a little bit more formally with the statistics that we've been building so far. All right, so if you notice on your calculator, your TI, when you do your linear regression t-test for the previous section, oftentimes it gave you some sort of equation like this, and it defined the variables that you needed, or the constants that you needed. All right, and in this section, we're going to go through and we're going to extract those constants that we need. That way we can build this equation of the line. All right, so the graph of the regression equation is called the regression line, or in other words, the line of best fit. So you did hear me talk about the line of best fit in the previous section when we were talking about correlation. Now is when we're actually, again, defining this regression equation or this regression line, and we can also use the term that line of best fit to describe that line. All right, now, x is always going to be your explanatory variable or the independent variable, and then y is going to be the response or the dependent variable, however we want to view it. Independent and dependent are what we refer to them in algebra class, and explanatory and response variables are what we refer to them in statistics. All right, so the regression line, aka the least squares line or the line of best fit, this is going to be the line that minimizes the distance between the points and the line. It best fits the data points. All right, that's why it's called the line of best fit, because it's going to fit all of the data points and it's going to minimize the distance between that line and all of the scatter plot points on the graph. Now in here we again have the line of best fit, this regression line, which is b naught plus b1 times x, where the point x bar y bar will always be on the least square line. So x bar y bar, this is kind of like that midpoint that we observe for this line, all right, or the midpoint for the data set values that we're going to be looking at. Now b1 or b sub 1 here, b sub 1, if you look at this original equation right up here, b sub 1 we said was the same thing as m, where m stands for the slope from our algebra class. So guess what b sub 1 is? You guessed it, this is your slope. In other words, this is your average rate of change. Nice. Well, B naught, or B sub 0 here, that was this original value, this original constant from an algebra class, which means that this is just my y-intercept. Alright, so nothing too bad. Alright, so this actually will explain that if x is equal to 0, that means that predicts the initial y value. Alright, and again, that's if y is equal to 0. Or sorry, if x is equal to 0. Nice. So once we have all this, we're going to figure out a ways to calculate these different slopes and these different y-intercepts. Now, there is a technical way to calculate all of this, and it involves using the standard deviation for the y values and the standard deviation for the x values. Typically, we're going to be given ordered pairs, x's and y's. Now, just really quickly looking ahead, look at this example down here. We have x's and we have y's. If we do x's in one list and y's in the other list, then we can naturally extract what is the standard deviation for all the x values and what is the standard deviation for all the y values. And that's what this here is referencing, this formula. Standard deviation of the y values divided by standard deviation of the x values multiplied by the correlation coefficient r. This should get us our slope. The y-intercept is then found by taking the average of the y values. That means we would take all this average of these y values down here, subtract it by b1 times x bar. b1, again, we found it over here, multiplied by x bar, but x bar is just the average of all the x values. So there is a mathematical way to extract all of these if we had to do it by hand. However, I am not going to require to do these. I'm not going to require you to do these by hand. All right. So that's very, very specific that you guys do need to know that this is not going to be done by hand. Instead, we're going to use the TI-84 to help us out. All right. Perfect. So again, the round-off rule that we're going to be using, I'm going to highlight this in red because again, it's going to be super important. We've used the round-off rule for a good while now. If you go back and look at your notes, the round-off rule is always stated in almost every single section that we work in. So below is a sample of 5 patients at a hospital with the given information regarding their height and weight. Part A, describe the relationship of the data using the scatter plot given. Alright, so let's look at the scatter plot down here. Alright, so we got the scatter plot down here. Now all we need to do now is just describe this. So we're going to describe this using all of the relationship terminologies that we developed in the previous section. So what type of correlation does this have, or does it appear to have? Right? Let's see the ruler. Does there appear to be a linear correlation? Yeah, it looks like there appears to be some sort of linear correlation happening here. All right, so I'm just going to draw my line here. So this does appear to be linear. I'm going to say linear correlation. Okay, now what else? Well, this line, as x increases, y increases, so we can say this has a positive correlation. Alright, pretty good so far. So linear, positive correlation. Now one more thing, is it strong, is it weak, or is it moderate? Well, at this point in time, since we only have 5 data values, I'm going to say that this is either moderate or strong. And the reason I'm saying this is because we only have 5 data values, and within 5 data values, it's really hard to then extract, is this moderate, is this strong, or is this even going to be weak? All right, but at this point in time, it kind of looks like it's going to be moderate / strong. So these are the terminologies that I want to use, or the terms that I want to use to describe the relationship between the scatter plot. All right, so part B. Find the correlation coefficient, in other words, the test statistic, and determine whether a correlation exists. All right, so we got a few things to do here. So it's asking me to find a correlation coefficient. So that's one of the first things that I'm going to identify here, that I have some correlation coefficient that I want to extract. All right. So for the correlation coefficient, I'm going to need to do this on the calculator. So I'm just really quickly going to write this in green because this is going to kind of be like a note that says use TI-84 to find R. Because you remember, R is that correlation coefficient. So what I need to do at this time is I need to go to my TI-84 and I need to start inputting these values into the list, into 2 different lists. That way I can find that correlation coefficient. So take out your calculators and I'll take mine out and then we'll take it from there. All right, here's my TI. Now again, I want to edit the list. So I'm going to just click Stat. Remember, statistics here, go to Edit, and we want to edit the list. Again, my 2 lists are from the previous section, so I'm going to go ahead and clear them. Tab on over, up till you highlight list 1, press clear, and then enter. There we are. Scroll over to list 2, go up, highlight list 2, press clear, and then enter. There you are. 2 lists cleared. Now we need to enter the list here, so that's going to be 67. That's going to be 72, and I'm entering all of the heights first. In other words, all of the x values. 77, 74, 69. There we are. All right, so we got 5 items on that list. Scroll over to list 2. List 2, the first weight is 155. The second one is 220. The third one is 240. The next one is 195, and the next one is 175. Oops, excuse me. There we are. Awesome. So 5 items on each list. Once you're done inputting them onto the lists, then you want to quit out of this screen. So we're going to press second, exit. All right, perfect. Oops, no, don't hit second anymore. Perfect. All right, so what I'm going to do now is I'm going to run a linear regression t-test. All right, so what I'm going to want at this point in time is I'm going to want that, oops, excuse me. Let's clear that. I don't know what that is. There we go. Okay, so here what I'm going to want to do is I'm going to want to go over to stat, and I want a test. So scroll over to test. There we are. And again, I want that linear regression t-test. If you remember, it's all the way at the bottom. So I'm just going to scroll up to take me all the way to the bottom. And here we are. That's category F. Press enter. Linear regression t-test. I'm using my x values as list 1, y values as list 2. Frequency, I just leave it as 1. This is a two-tailed test, if possible. All right. And I'm going to scroll down now to find my R value. So here's my R value. My correlation coefficient is 0.9031. Let's go back and write that down, so now that we found it. All right, awesome. Now we're back. So what I'm going to do at this point in time is I'm going to write my R coefficient. So R is equal to, oops, my apologies, 0.9031. All right, now if you remember, back in the previous section when we were running a hypothesis test, we said that we needed to identify what was those cutoff scores for my R values. Oops. Apologies here. So what were those cutoff scores? We went from -1 to 1, and again, these were for our R values, centered at 0. So I need to figure out which cutoff score there is here. That way I can determine whether there is a correlation or not. So how do we determine that? By using this R value. Well, we could either use the bell curve to determine that this is a two-tailed curve using that t-test, or we can use table A5 to determine what is that critical value that we need. I want to use that critical value method, right? So let's go over to table A5 and let's use everything that we have so far. What is our n value before we proceed? So our n value, well, how many ordered points do we have? 5. So n is equal to 5. We don't have a significant level given to us, so if it's never given to us, what do we use? 0.05. Awesome. So let's take these two things now and let's go over to table A5. Alright, so here's this formula card, and again, just go to table A5. Here we are, table A5. Let me zoom out just a little bit more. There we are, table A5. So again, we're going to go with our n value. The n value that we were looking at was an n value of 5, and we were using a significant level of 0.05, which means that intersection is here at this specific critical value of 0.878. So all we need to do now is go back and write this test, or this critical value, in order for us to conclude that test. Alright, here we are. So I'm going to write my test statistic, or sorry, my critical value here. So critical value I'm going to use R is equal to, and that was 0.878. Alright, and again, this was from table A5. So I'm going to find that now. Alright, let's say it's somewhere here, -0.878 and 0.878. So anything within the shaded region right in here, both of those shaded regions, anything within those shaded regions is going to be considered to have a strong correlation. Alright, so as we then start looking at this, my value R is equal to 0.9031 lies right in here. Which means, is there a correlation? Yes. How strong is it? Well, it's very strong, because this correlation coefficient is fairly close to 1. So does there exist a correlation? Yes, there exists a correlation, and it is strong. Alright, so what I'm going to do is I'm going to summarize that here. Alright, let's see what I can do here. I'm actually going to move this. Let's move this over here. There we are. And then I'm just going to summarize here. I don't know why it zooms out. There we are. There is a linear correlation. So that's my answer there. Alright, and again, not just by looking at the picture, or not just by looking at the scatter plot, we want more mathematical representation behind it. And this is the math that goes behind it in part B, to be able to fully assert that there is some sort of linear correlation. Alright, perfect. Now, we want to find the line of best fit. So that is what we're going to be looking at next. Now, remember, the line of best fit looks like this up here. That was our y hat is equal to b sub 0 plus b sub 1 times x. Alright, so let's extract this. And the only way that we're going to extract this is from the TI-84. Use TI-84, and I'm going to say linear regression t-test. is what you have to access. So let's go to the TI and let's start extracting this line. All right, here I am. Now, luckily for me, I didn't clear this. This is, again, still using list 1 and list 2 for the linear regression t-test. Now, look at this right up top, that equation. That equation is y is equal to ax plus b. In other words, it's giving you that linear equation. But for us, what is a and what is b? Well, if you look down below just a little bit more, you're going to see the value of a and you're going to see the value of b. In other words, your calculator is automatically giving you the answer, which is nice. All right, so what I'm going to do is I'm going to take these and I'm going to write them over on my sheet. All right, so follow me along. All right, awesome. So again, in here what I did is I took a quick screenshot and I'm going to use these values now. So what I have here is y hat is equal to, let's say, my y-intercept. Y-intercept in this particular instance here, it's giving it to me as my a value. So my a value is just this one here. All right, so let's go ahead and let's write that down. This value is -359 point, we'll say 79, like such. All right, and then plus B1, well, B1 is my slope. That's my slope that I was defining. My slope on the TI-84 is denoted as B, which means my slope here is 7.75. 7.75, and then I need my x variable, and there we are. There is my slope, or sorry, there is my linear equation. So this is what I'm looking for on the exam. Can you give me a linear equation? Now, naturally, you can extract the linear equation just by using the calculator, which is really, really awesome. All right, so again, all I'm doing here is I'm taking this a value, and that goes there, and then I'm taking this b value, and that goes there. That's all there is. That's all there is to it, folks. Just like that. All right, so make sure you're extracting the linear equations correctly from the specific calculator screenshot that you're observing. All right, now this also says to sketch it below, and we actually already sketched it here. Now, some of you might actually be saying, well, hey, Mr. Castro, there's something wrong with this, and the reason why it kind of looks wrong is because this y-intercept should cross this vertical line, or my y-axis, at the point -359.79 for the y value, and the x is 0. Well, the problem here is that this bottom left corner is not the origin. If we were to keep extracting this picture further and further and further so that we could see the origin, the point 0, 0, then this blue line would naturally be below that origin line. All right, so everything is fine. There's no mistake. It's just that the bottom left corner is not the origin. All right, so now let's go ahead and let's look at the slope. Now, we want to interpret the slope. Now, in order to interpret the slope, what I'm going to have you do really quickly is I'm going to have you recall what we look at the slope to be back from algebra class. The slope is really your rise over your run. Okay? In other words, it's your y values over your x values. Oops. And again, what we're going to do is we're going to grab the change in y's and the change in x. And what we're going to do here is we're actually going to be interpreting certain units of measurement. So what I want now is my slope. What I'm going to do, my numerator, I'm going to look at my y values and I'm going to extract what is the unit. So all I'm going to say here is units of the y values divided by the units of the x value. The division bar, it's going to mean per. Not the cat purr, but per, as in miles per hour. Alright, so anytime that we're asked to interpret the slope, we then go into this interpretation right here. What are the units of the y value? Per the units of the x value. So when I try to get the interpretation, this is going to be pounds per inches, because that's my y values, which is in pounds. Division means per, so pounds per, and then the units of the x value, which is inches. Awesome. So for this particular question here, when we look at slope, slope is going to be in pounds per inch. And I used abbreviations here, LBS and IN. LBS for pounds, IN for inches. So pounds per inch. So let's now look at this. Interpret the slope. This is going to tell me that for every inch increased, we would expect a person to weigh approximately 7.754 pounds more. Now, where did all of these numbers come from? Well, my numbers here, they came from my slope. What was the slope that we were looking at first? Well, the slope that we were looking at is 7.75. I could naturally get rid of this 4 since I didn't include the 4 initially. We could just do 7.75 and everything is peachy keen. So, 7.75, what does this mean? Well, 7.75 is really being divided by 1. Even though we never denote that it's being divided by 1, we can always assume that any number is always being divided by 1. Since that's the case, well, let me actually redo that. Since that's the case, what we want to do to say this, to interpret the slope, we start with the explanatory variable. So, what's the explanatory variable? It's the height. So for every inch increased, and that's your explanatory variable, what's happening to that explanatory variable? Well, for every inch that we increase, then we would expect a person to weigh, and that's now talking about your response variable, weigh approximately 7.75. That's this guy right here, more, 7 pounds more. So for every inch that you increase, you'd expect a person to weigh 7.75 pounds more. So there is a linear correlation between height and weight, and typically this is what we use in order to make those assumptions or those interpretations. So now that we have this, check out what the next part says here. So this is the next page right in here on the left, and it says the interpretation of the slope, what we just talked about. For every unit increase in the explanatory variable, that's what we just did, on average, there is an increase or decrease slope amount units in the response variable. And that's what we did when we were describing all of this. Alright, so when the explanatory variable is 0 units, on average, the response variable is, and we're going to say this is going to be the b sub 0 units. Whatever units we have is going to be the units that we're going to be looking at when we're talking about the interpretation of that y-intercept. Alright, awesome. Now, let's look at this example here. And with this example, we're going to use the exact same thing that we used before, which is going to be that linear regression t-test. So I want you to take some time and read over the example really quickly, get yourself acquainted with the example, and then we're going to go ahead and start it in just a bit. Alright, so here we go. Now it says recall the exercise from the last section in which we concluded that there was a significant linear correlation between the average saturated fat consumed per day and the cholesterol level of 10 men. So this data was actually given to us before in the previous section, and we're going to continue working with this data set in this particular section. So for part A, what we want to do is we want to find the regression equation where X is the average daily fat consumption in grams of a man and Y is the cholesterol level in milligrams per centiliter. All right, so I need that I need that linear regression equation, that line of best fit. The way I'm going to get that is by using my TI. So let's go back and let's use that TI. So I want you to take some time and to input all of these into a list. So your first row is list 1. So list 1, when we talk about list 1, is the fat consumption in grams. All right, that's his first list. List 2 is going to be the cholesterol level in milligrams per centiliter. All right, that's list 2. Make sure you enter both of these lists and you have both of them ready to go. And what I'm going to do is I'm just going to quit this, second quit. And I want, again, to run a test. So I go to Stat, scroll over to Tests. I'm going to scroll up so that I can find linear regression t-test. And I'm going to run that. List 1 was my X values, in other words, my explanatory variable. List 2 is my Y values, in other words, my response variable. So, two-tail test, that's fine. Calculate, there it is. There's the moneymaker. So, I just want to quickly look at my R value. Look at this R value. Very large correlation, which is nice. Alright, so I'm going to scroll back up, and this is a part that I need. So I'm going to take some time. I'm going to actually take the screenshot over to our work, and I'm going to use that screenshot there. So let's go back to the board. All right, so here we are. Now, what I'm going to do here is, again, this is actually giving me my linear equation here. So all I'm going to go do is I'm going to grab this linear equation. So y hat, now I'm going to go with my y-intercept first, and that's my a value. So my a value here is just 1.06.11. All right, so I'm going to use 106.11. There we are. That was my y-intercept. Now I need my slope. My slope, according to this equation, is b. So my slope here, I'm going to use as 1.59. So this is going to be 1.59. There we are. And this is going to be x. Don't forget the x, because the x actually lets us know that this is your slope. The slope is always multiplying that x value. Awesome. So find the linear regression equation where x is the average daily fat consumption. This is just telling us that this is going to be your explanatory variable, in other words, L1. So all of this was L1, and then this also tells us of a man of y, and y is a cholesterol level in milligrams per centiliter. That means I was list 2. Once we enter this, we use the linear regression t-test. Oops. Linear regression t-test, and we extract what we have given here. All right, so interpret the slope in the context of this problem. All right, so again, our interpretation is right up here. So we want this interpretation of the slope to occur. So we're going to use this interpretation right down here. And we're going to start by saying, for every increase, or I'm going to say for every unit increase, in, and then we go with the explanatory variable, that was in fat consumption, we would expect a man's cholesterol level to, and then look at your slope. Is your slope positive? Yes. Well, then that stands for an increase. We would expect the cholesterol level to increase on average 1.5 1.59, and again, on average, our slope, 1.59. There we go. Or let's put units of measurement here. 1.59, and this is going to be milligrams per centiliters. Milligrams per centiliters. There we are. That's all there is. So, finally, part C. We then say, now we want to predict the cholesterol level of a man who consumes 65 grams of saturated fat per day. All right, so if a person or if a man consumes 65 grams, we now have to predict. So there is a very, very big key word here, and that is predict. So we want to make an educated assumption about what will happen. Well, in order to predict accurately, if there is a huge correlation, meaning if there is a big correlation, then we're going to use the linear regression equation. If there is not a correlation, we cannot use the linear regression equation for a prediction. All right? So, does this have a high correlation? Does this data set have a high correlation? Yes, it does. The scatter plot, or the data given, has a correlation, and that's because we figured out that R, that correlation coefficient, was 9.9079 from before. Or if you go back to your calculator and scroll down just a little bit, you'll see the R value, which is going to reflect a really high correlation. Now, since that's the case, what I'm going to do is I'm going to use my Y values, or my equation, as a predictor. So what I'm going to do is I'm going to insert 65 grams into my equation here, 106.11 plus 1.59 times 65. Because that's the X value that I have, that they're giving me. The 65 grams corresponds with my explanatory variable, so all I do is insert. Once I do this, I'm going to go to my calculator and I'm going to insert everything as I see it here. Alright, so follow me along to the TI-84 and we'll go ahead and we'll make those insertions into the calculator and observe. Alright, here we are. So I'm going to go ahead and exit out of here. There we are. So I'm going to insert 106.11 plus 1.59 times 65. There we go, exactly as it was. Press enter, and there's my answer. 209.46. Let's go back and let's talk about that. 209.46. There we are. So I get 209.46. Now, what does that mean? Well, this is our prediction, right? So since this is our prediction, what we're going to do is we're going to write up a conclusion here. So I'm going to say, I don't know what I'm going to say with that. There we are. Okay, so in here, now I'm going to say, we would expect that a man who consumes 65 grams of saturated fat to have a cholesterol level of 209.46 in milligrams per centiliter. And that's a prediction for it. All right. So again, we can only use the linear equation if we know that there's a high correlation. If you get that there is no correlation, then we can't use it. So let's go ahead and let's summarize right below here at the bottom of the page. That says, if there is a significant linear correlation between X and Y, then we're going to use the linear regression, linear regression equation to predict the y value given for a specific x value. Now, in the bottom part, if there is no significant linear correlation between x and y, so again, if we run our linear regression t-test, and once we do that critical value method to check whether there is a correlation or not, and that critical value method is part B on this first example, we have to do that in order to make sure that there is a correlation. If it falls outside of the friend zone here, there's no correlation. All right, so once we run this test and then we come to the conclusion that there is no correlation, then the best prediction of y is going to be the mean of the y values for any given x value. Now, this is kind of important because, again, we're not really making a prediction if there's no correlation. All we're doing is we're just saying, hey, on average, this has been the outcome. So if we don't know that there is a correlation or not, again, we don't want to use that linear regression we don't want to use that linear regression equation because it can give us false information. The only thing that we can use if we don't have correlation is just take the average of all of the outcomes or the response variables, in other words, your y values, and just say, hey, on average, this was happening. So if there's no correlation, on average, you're going to expect this to happen. All right, so that's for this part. Now let's try to summarize all of this together. All right, so here we go. Let's try to work on this example. We'll get started in just a bit, so read through it. All right, so here we go. We're going to be looking at this example that says the following are fat and sodium content are fat and sodium content related in fast food. So here are the fat and sodium content for several brands of burgers. All right, they have total 7 brands of burgers. So 1, 2, 3, 4, 5, 6, 7, and we have fat given to us here in grams, and we're going to have sodium given to us in milligrams. And we now want to use a 0.05 significant level. All right, so that's one of the important items here to determine if there is a linear correlation. All right, so now I'm going back into that linear correlation process between fat and sodium content in burgers. All right, so that's going to tell me now that row 1 I'm going to interpret as list 1, row 2 I'm going to interpret as list 2. That way I can extract what is going to be this R value that I'm going to be looking for. All right, so really quickly I want to state a null and alternative hypotheses. So the null hypotheses and the alternative hypotheses, the first one is going to be, because we're looking at a linear correlation, we're going to assume that there is no correlation. All right, that means that my alternative means that there will be some type of correlation, and that's what I'm looking for. All right, this automatically makes this a two-tailed test. Now, if you've noticed, all of these linear correlation problems, hypothesis testing wise, are always going to be two-tailed test at all times. All right, perfect. So what I'm going to do now is I'm going to insert all of this into the calculator, and I'm going to extract everything that I need. All right, so let's go through the calculator, let's extract it, and I'll bring that screenshot here. All right, so I took the liberty to input all of the values. So list 1 is at row 1, list 2 is at row 2. Once we're done with this, we're just going to go ahead and run a linear regression t-test. So here we are, test. Oops, excuse me. Wrong test. Here we are, test. I'm going to scroll down to linear regression t-test. There we are. List 1 and list 2, frequency 1, and then that's a two-tailed test. Calculate. There we are. So what I'm going to do at this point in time is I only want to extract, at this point in time, I only want to extract my R value. All right. Now, when I extract my R value, I'm also going to be looking at my test statistic and my p-value. All right. So let's extract all of that, and then we'll go ahead and we'll put all of that onto the screen before. So follow me along. All right. So here we are. Now again, I want to use the critical value method. If I want to use the critical value method here, then what I need to do is I need to find my critical value. Now the critical value that we then search for is going to be based upon my n value, which in here is 7, and my significance level of 0.05. So let's go back and let's go ahead and find that critical value on our table. That way we can extract what it is that we're looking at. Alright, so let's go back to table A5. Here we are. Alright, good. Now we're looking at n is equal to 7. Alright, so n is equal to 7, alpha is 0.5, which means my level of, my critical value should be 0.754. So we're going to go ahead and write that down on the previous screen. That way we can start working with it. Let's go back. Alright, here we are. So let's see from table A5, we get that R is 0.754. So I'm just really quickly going to write it on here. So about halfway, a little bit more. So somewhere around here. So 0.754. Same thing here, 0.754, and that's negative. And again, our rejection region is right in here. So now I need to see my test statistic. My test statistic, what we're looking for is going to be my R value here. I'm going to call this R star. And that one's going to be this one down here that is given to me. So I'm going to bring this up here. And that one is 0.199 as such. Alright, so if it's 0.199, then that means 0.199 is somewhere right in here, 0.199, which means at this point in time it does not fall within the rejection region, so that means we must not reject the null hypotheses. This is going to tell me that there's not enough data to support my alternative. So I'm going to say fail to reject the null hypotheses. Alright, now what if we wanted to use a p-value test? Well, if we wanted to use a p-value test, we would then just go to our test statistic. The test statistic here would be, and let's see if we can find it here. Let's do this in another color. Let's do this in purple. There we go. So my p-value, I would look for my p-value, and here it is. So my p-value in this particular instance, if I was using the p-value test, my p-value is 0.6687. My alpha level is 0.05. Remember, if the p is low, the null must go. But in this particular instance, the p is not low. The p is actually larger. So if the p is larger, the null must not go. So therefore, we must not reject the null hypotheses. All right. So that's a way that we're using this for the p-value method. The p-value, again, automatically given to you here. There's no need to go through and calculate it because we're automatically going to be given that p-value. Alright, so that's why we need this linear regression t-test. So remember, this screen actually gives us a lot. It gives us the p-values, it gives us a linear regression equation, it gives us the degrees of freedom, it gives us standard deviation, it gives us almost everything that we need. Alright, so conclusion. What is our final conclusion? Well, I'm going to say that there is not sufficient sample evidence to support that there is a linear correlation between fat in grams and sodium consumed. Sodium in milligrams consumed. So again, just based off of the data set, All right, so again, we're basing this off of the data set. We're not basing this off of any bias that we have. All right, remember at the very beginning of the course I said we're going to leave the bias at the door and we're only going to trust the math, the facts that we see. All right, so at this point in time, again, there is not sufficient sample evidence to support that there is a linear correlation between fat in grams and sodium in grams consumed. And one last thing I'm going to say, at alpha is equal to 0.05 significant level. All right, so now that we got that conclusion, let's look at part A. Part A says, what is the regression equation and is it helpful in this situation? Why or why not? All right, so let's go ahead and let's look at that. Well, what is the linear regression equation here? In order to answer that, we need to go to our first screenshot here, and we're going to use A as our y-intercept. So that's 930.02 plus, wow, that 02 looks very bad, 0.02 plus, and that's going to be my bx, so b is 6.08x. So is it helpful in this situation? It is not helpful. Why not? Because there is no correlation. So it is not helpful because there is no correlation. So if we look at part B, where we want to predict the sodium level of a burger with 25 grams of fat, I'm sorry, we cannot use this equation. So here we cannot use y hat is equal to 9.30.0, or sorry, cheese and crackers. Here we go. We cannot use this equation simply because there is no correlation. So be very, very careful with that. Instead, we have to use y bar. In other words, the average of the y values. So how do we then find the average of the y values? Well, we need to go through that and we need to find that out. So let's go through and let's find the average of the y values. All right, so I'm going to go back to the TI and we'll talk about it there. All right, here we are. So what I'm going to do is I'm going to find the average of the y values. So I'm going to exit out of here. So second, quit. And again, what I want to do is I want a statistic here. So I'm going to press statistics and I'm going to go over to calculate, and I want a one variable statistic on my y values. The list that contains my y values for me was list 2. So I'm going to press second 2, and that acts as list 2. I don't have a frequency list, so I'm just going to press enter. Here we are. Look at that first one here. X bar. Now, again, it gives it to us at X bar, but we know that it stands for our Y values. So in other words, that is Y bar. So this is the value that I want to see, and that's the value that I want to use. So let's go back and let's go ahead and write that down. All right, so here we are. So again, I put the screenshot here that says we use one variable statistic on list 2, and that was because that list 2 contained our Y values. And so now the values that we need are right here. So to predict this, I'm going to say if a burger, there we go. So if a burger has 25 grams in fat, we would expect its sodium content, or its sodium content, or let's say its sodium level, to be approximately, and then that's going to be this number here, 1138.57 and then we're going to put units of measurement here, where I believe it was in milligrams, if I'm not mistaken. Yes, sodium was in milligrams. Approximately 1,138.57 milligrams. And that was that value right there. And that's all there is. That's all there is to it. All right. Now, down here, down below, you have a few more instructions as to how to use that calculator when you want to view the dot plot, or sorry, when you want to view the scatter plot. That process is down here. Now, typically in my class, I don't like viewing the scatter plots too much, which means we're just going to do the number sense behind it. We're going to find out what do the numbers mean and what do they represent. All right, so this actually wraps it up for section 10.2. So I hope you all enjoyed the lesson, and I will see you all for the next lesson. Stay safe.